There we go. Okay, good morning, everyone. We're starting. So, last time we were speaking about, let's see, there we go, good. Last time we were speaking about, we had an introduction, mentioned the fact that in order to do numerical computations and analysis and in order to be quick, let's say, and use more advanced tools for this course and especially in the future, then we need to learn to use some numerical and scientific libraries. For Python, NumPy is the first one, the basic one, the one that gives us the numerical part, of course, as the name implies. So we have been speaking about these new types and the difference between an integer and a regular Python integer and a new NumPy integer, which is characterized by the fact of having a fixed width in terms of bits. So I had left a question hanging last time. How many bits do you need to store this number here? Okay, how do you figure out how many bits you need if you want to represent this number in binary, right? And does anyone have a clue now? Okay, let's start. Okay, so first of all, a small refresher. Here is what I'm talking about. These are 4 bits. We said with 4 bits, the best you can do, I mean, in terms of representing positive integers, let's say non-negative integers, I would say, which are called unsigned integers in technical jargon. The best you can do with 4 bits is this. So you start from 0, you interpret them as binary, and you reach up to 15, which is 2 to the power of 4 minus 1, where 4 comes from the fact that we have used 4 bits, of course. So with 8, you can get at most to 2 to the power of 8 minus 1, which is 255. Yes, exactly, precisely. It's the logarithm in base 2. Okay, just like you would use the logarithm in base 10 in order to see how many digits you have here. Okay, if you, I mean, in case you don't really believe me, there's a very, very quick thing that you can do. So think again in decimal and just say 1, 10, 100, 1000, and so on, and say how many digits do you need to write down these numbers. It's 1, 2, 3, 4, and so on. And clearly, this is the log in base 10 of your number that you're trying to write down. Okay? Sorry, plus 1. So this is, okay, there's a plus 1, but it's essentially it's the logarithm. Okay? And, well, if now you interpret the ones on the left as binary, then you just substitute the 10 here with 2. That's it. Okay? So this is just something that I left hanging there last time. So there we go. Then, what else? Yes, so we studied this, and then we said, okay, now these things are used because we actually, the main object that we have, new kind of object, is arrays. Okay, and arrays, one-dimensional arrays are sort of like lists, but more efficient for numerical computation. So in order to understand why this is true, we need to, sorry, we need, oops, this thing, good. We need to think about the hardware and why these these NumPy arrays are more friendly, let's say, so to speak, to the hardware than regular Python lists. Does anyone have an idea before we start? No? Okay. So, of course, I haven't explained what a NumPy array is, but it's the same story with regular arrays, if any of you know about those. Okay, so the first thing that we should mention, what's this? Sorry. First thing that we should mention is, it's a bit trivial, but it's important. Everything that your computer, that your CPU, the central processing unit, operates on resides in memory, in the RAM, okay? So whenever you, even if something is on your disk, it's first copied into RAM and then worked on from there. So, which means that we are going to, say, think about how RAM, the computer memory, is organized. Now, okay, so you can think about RAM, you can conceptualize it as a long list of slots, okay? Something like this, and it goes on. And each slot here is 1 byte, so 8 bits, okay? Something like this. This is the, let's say, modern computer arrangement, okay? The one that is ubiquitous nowadays. It's for historical reasons that we use 8 bits. It's not something, I mean, necessary. There had been attempts in the early days to use different amount of bits, but now everybody has settled on this, basically, this format. And so all of our computers now and cell phones and whatnot, they use this arrangement. Second, yeah, so this is contiguous, and so you need to imagine things like that. Inside here, there are, I mean, a few patterns, say 0, 0, 1, 1, 0, something. Okay, it doesn't matter. There are 8 bits inside of each slot. So, having said that, suppose now that you wanted to have, let's say, a list, right? Not a Python list, I'm speaking, but we can use a list of numbers. But say, let me call it a sequence, so to be agnostic with respect to what which object we are using in the programming sense. So let's say that we have a sequence of numbers, and it's something like 3, 4, 15, 7, I don't know, something like that, okay? Whatever you want. A sequence of numbers. Let's say 4, it could be 4,000, okay? By the way, one thing that I haven't said, but it should be, I mean, I'm sure you know it, it's that the number of slots here, it's in the order of the billions, okay? So there are quite big, this space that you have. There's lots of space in modern computers, okay? It's a gigabyte is essentially a billion bytes, so a billion of these slots. Okay, so again, we need to store these 4 numbers somewhere in sequence in the RAM. What's the most obvious way to do it? It's obviously, you just put 1 number per slots, essentially, okay? Something like that, if you can. That's just the most natural thing to do, which means that here, at some point, look at these numbers. You could represent them. So now I'm going to enlarge the slots because otherwise they won't fit. So here you would have, say, for example, 3. It could be represented, as we said, with 8 bits. You represented that like this. Okay, so, and then you have the rest. And now I'm going to say that this pattern of bits represents 3 in my intentions, and this is 4, and this is the equivalent thing for 15, and this is 7, okay? So this is more or less what you would do, right? So, couple of questions. Okay, this is the contents of the thing, but you need to imagine that inside the RAM, there are other bits before and after everywhere. It's not blank. There's always bits there, some kind of bits, maybe random ones from the initialization, maybe zeros, maybe something from an early computation, something is there, okay, at this stage. So the other thing is, in this representation, you need to know at least a couple of things, essentially, where it starts and where it ends, right? Because otherwise, so you need to know that this is the start and this is the end of the thing, of the storage that we're interested in now. The way you do it normally is not to store the start and the end, but rather to store the start and the length, which is, of course, completely equivalent. So somewhere you want to, I'm sorry, somewhere there must be the information about the fact that this is the first point in the sequence, this slot here, and secondly, that the length is, in this case, 4. Okay? Good. So, one question arises, how do we, in what format do we store, how do we, here I've drawn a little arrow, how do you, this information that I've been speaking about, the starting point and the length, of course, also must be inside the RAM somehow, okay? And so, did I record the session? Yes. Oh, good. Sorry. Just sorry. I was saying yes. So everything must be stored inside the RAM. So the length is again an integer, and we know. Let's say we can speak about that, but it's clear that at some point we could store, say, the number 4 here in front, okay, somewhere, and say, okay, the list starts here, the previous slot contains the length, and then that amount of slots contains the data. But how do I encode this arrow here? How can I write, essentially, how can I take that, what I mean as an arrow, and put it inside memory? How do I represent an arrow? Anyone? How do I represent the information about where the thing starts? Any guess? Sorry? Indexing, exactly. So the answer is easy, but it's powerful. It's a very powerful idea. It's the idea of pointers or references in computer science. Okay, so the thing is, as I said, the RAM can be thought of as a sequence of slots, and therefore you can just give a number to each slot, 1, 2, 0, starting from 0, of course, as usual, 1, 2, 3, 4, and so on, up to some billions. Okay? Now, these are integer numbers, and which means that you can encode that in binary somehow. And therefore, you can put that information somewhere here, for example. Okay? Yes?
But when I try to achieve like the third spot?
The 15, you mean?
Yeah.
Or the...
Whatever, like, number we stored there.
Sorry?
Whatever the number we stored here, like I'm trying to get it out of the RAM, like I'm trying to read that.
This one, you mean?
Yeah.
Yes, good, yes.
And you've also stored the length somewhere in the RAM.
Yes.
But how does the computer know that that number represents the length?
And then the other. Yes, good. Good question. So here's the thing. Let me see if I can explain. More or less, it's the answer is complicated. Okay, so it's a good question with not. It doesn't have an easy answer. So let's think in terms a little bit more abstractly. Okay, this is the RAM, and I'm not now dividing it in slots precisely. I'm just representing it as space, and then I'll say, okay, somewhere in the RAM, there's a region somewhere, okay, there, which is essentially Python executing, okay, the things that Python is doing, and there's a program which is managing that and knows what is where, okay. It started off in a predefined condition, and then it started populating the thing in a way in such a way that it knows when there's a pointer, when there's one of these say it knows when there's one of these arrows, these indices that represent arrows. So as I was saying, this number here 2 is intended to represent this, okay, an arrow to some other position. So in this space, there are going to be arrows to various locations, maybe also inside, okay, doesn't matter really. Okay, so the Python interpreter is managing this thing. Okay, when you now say create a new object and you want to give it this sort of arrangement, the interpreter at some point stores an index here, knowing what kind of object it is. So for example, it could be, I know that this position in the RAM here has an integer that represents an address. It's called an address, which is an index in RAM. So you can think of it as an arrow, conceptualize it as an arrow. It contains the address of something which is an ND array. Okay, and because it knows that it's an ND array, it knows that the bits starting from this position here, okay, the bits there start off in a certain predefined arrangement, which has been specified by those who have created the ND array. And this pre-specified arrangement is essentially this. There's a little bit of an initial part. So let's say that here we have an ND array. Okay, the kind of object that we are trying to figure out how they work. Okay, so there's an initial part, and we are saying, let me color it slightly differently. We are saying that this is called a header. It's not, it's a term that I came up with myself. It's not, it's not from the builders of the library. And then the header has some sort of pre-specified format. So in the format, there are a few information. There are some information, and part of this information is the length of the thing, the length of the data, the amount of data. Okay, so in the previous example, this would be 4. Now, there's more information there, and I will speak about that later, but let's stick to this simplified example right now. Okay, so the information there would be length 4. So, for example, here in this region here, that could be the first byte or a few bytes or whatever, a pre-specified amount of bytes tell you the length. The length. Okay, and then something I haven't told you, but it's important, is the type. Okay, so it means how do we interpret the following data. In the previous example, I have said, I started off by saying each slot is a single integer. And this is 3. This, for example, could mean that the type that, in terms of what I said before and in last lecture, that this slot is of type int8 or uint8. So if I'm saying the type is uint8 or int8, it means that each element requires 8 bits, and so I need 1 byte, and so for a length 4 array, I need 4 bytes. If, on the other hand, the type were, for example, uint64, then it would mean that you needed 64 bits for each element, and then 4 elements require 4 times 64 bits, which is 4 times 8 slots, 8 bytes. 64 bits is 8 bytes, 4 times that, 32 bytes. Okay, so if you want to use larger integers, you, of course, need more storage for the same amount of, the same length of the array. And therefore, in the header, in order to know how to interpret how much memory this thing actually occupies and how it's organized, you need to know this information about the type, right? Obviously. So there's the length, there's the type, and then what I told you before in the previous example is that this red thing here is essentially the data. And the data can have a variable length, but the length can be known from the header. okay? And also how to interpret the things in there. Good? Okay, there's a slight complication. There are a few slight complications that we will speak about in a second. So we will revise a little bit this picture, which is essentially the basic thing, and then we'll just add a little more things to that, because actual ND arrays are a little bit more sophisticated than that. This would be a good description for a standard so-called array in computer languages which have them natively, like C. I don't know. Well, not really. The header, you need to store it yourself in that case, but it doesn't matter. Yes, so why is this efficient? Well, this is kind of obvious, this arrangement, and this is the reason, because the RAM is built in this way. Not the part about the header and all of the rest, but just the part about storing the numbers there in sequence, one after the other, right? That's not surprising at all. It's the natural thing to do. So why do we need ND arrays, and why doesn't Python do this already? Why do we need this extra library? In order to understand this, I think it's useful to think about how you would store the same sequence of numbers if instead of an array, you were trying to build a regular Python list. Okay, so let's think for a second about, again, the RAM with its arrangement in slots. So long tape, essentially, of something, of space. And then suppose that you have a Python list that's 3, 7, 15, whatever, okay, 4, something like this. Okay, so can we do the same thing with regular Python list that we just did before? Can we just store, say, however many bytes we need for the 3, and then however many bytes we need for the 7, and then the 15, and then the 4? Can we do this? Sure, we could. There's a problem, though, that Python lists are very, very flexible. For example, I can take a Python list and substitute this 15 with 3 to the power of 100, if I want, right? And that, how many bits does that require? Many, many more than 15, okay? Whatever the logarithm base 2 of the huge number that we had was, okay? So even more than 64 bits, as we've seen last time. So let's say, I don't know, 100 bits, it doesn't matter. Okay, so if you have to store 100 bits, then what does this mean? It means that now, in order to modify this list, you would need to somehow fit. So these, let's say, were 8 bits because they were sufficient previously, but now I want to fit 100 bits inside in the middle of the list, which means that now this here needs to be moved somehow. Not only that, okay, is this clear? I have to make space to fit inside the bigger thing. Except that in the RAM, there's no way to make space. You need to copy over the thing. The only way to make space is take whatever was there, copy it 1 byte by 1 at the end, and then write in the new space that you have created. Okay, is this clear? Okay, so you need to somehow make space. Not only that, if these integers are all of the integers are potentially different number of bits, then how do you know to interpret this as a short integer, this as a short integer, but then this new one is a very, very big integer? How do you know that? If it's just bits, you remember that I'm representing things like this, but in the RAM it's all bits without separations. Okay, the only separation is in slots, and there's no markers or extra things there. Every information about what's in there must also be in there somewhere. Okay, so the information about how long is each element must now come individually, element by element, because each element in this new list with a big number in the middle, can potentially have a different length. Not only that, it could potentially have a different type. So it could substitute now 7 with a string hello, for example. Okay? And then this would mean that here I need to remove that 7. Maybe that 7 was represented as a byte. And now I have to substitute it with hello, which is at least 5 bytes, 1 per character. But again, it needs to make space. I need to move all the rest again to the right. And moving something to the right means taking all of it and copying it 1 byte by 1 byte. And so do all this copy operation and then insert this new information there, except that you also need to store the information that this is now a string and not an integer. Yes?
How do I know that I remove this stuff at the end of, maybe there is a useful list I'm trying to work with at the
Yes.
end of the RAM? Does it get lost?
The fact, yes, good. So the question is, for those at home, the question is, okay, I'm saying I'm moving stuff here on the right, but what if I had something here on the right before that I wanted to keep, right? Am I going to override that? That's perfectly valid concern, and indeed, there's the system, the operating system and Python itself, they need to know if there's something there. If there's something there which is already useful, then you cannot even do this operation, which is already expensive. You need to do an even more expensive operation, which is find another position in memory, in those billions of positions, find another position in memory which is big enough to accommodate all of the new list. Okay? And then you would move all of it, not just the end. Okay?
If all of these conditions are not possible, you get, what kind of error do you get?
A memory error, out of memory. Yes. Normally it's an out of memory error. If somehow at some point the Python says the operating system is not letting me get any sufficiently big chunk of memory, and I don't know what to do, it crashes. Okay, there's no recovery from that. Well, in Python you could catch the error and say, okay, try and do something else, but you simply cannot go on that way. Okay, so all of this shows you that this is not a good idea, essentially, okay? If for Python lists, because you want this flexibility, this is not a good idea. And so you cannot arrange Python lists this way, in memory. They cannot be stored in these compact, contiguous chunks. In order to make a little bit more precise the notion that this is not a good idea, let's say that the length of the list is n, okay? And let's say, given what I said, suppose that I'm now trying to overwrite an element inside the list somewhere, and that I need to do this operation. And that this operation has potentially the consequences that we have just seen, so to just need to make room, or if I delete something from a list, you know, you need to shrink it. I mean, the opposite thing is also true. If you had a big number and you substitute it with a small one, you need to shrink it, and so you need to copy over the right part to the left, okay? So how much does it cost, this operation of changing one element inside the list? How much does it cost in terms of the length of the list? Is the question clear? Suppose that I have a list of 4 elements. I'm now trying to change one element, maybe in the beginning, maybe in the middle somewhere. Let's say in the beginning. If I change something in the beginning, then I could potentially need to relocate 3 elements, which is the rest of the list. If I have a billion elements, and I change the first one, then all the other elements might potentially need to be relocated. And so this is the amount of stuff that I need to move around depends on the length of the list. It's directly proportional to the length of the list, which means that this is an operation of order n. So the longer the data, the more costly this operation would be, okay? And this is not acceptable. We don't like that. We would like to have an operation which is basically the same cost, no matter how long the data is, which in technically you call an operation of order 1, means independent on the size of the list. Okay, so the solution to this is arrows, references. The solution to this is to think, is essentially this. You conceptualize Python lists like this. there's somewhere, let's say, a variable with an arrow that points to some list, and then this list has slots, and each of those points to something. And that something is the actual data. This could be, I don't know, 3, this could be, let's say, 7, and this could be the string hello. And of course, what this means is that the new arrangement goes something like this, conceptually. So each of these arrows, remember, you represent that as an address in memory. And the addresses in memory, because the number of possible addresses is fixed, you only ever need 64 bits for one address. And therefore, you know in advance that each address can be stored in 64 bits, and you don't need to worry about having longer or shorter distances. So there is going to be 64 bits somewhere where there's the pointer, where L contains an address, which we conceptualize as this arrow, a reference, or pointer, if you want, a pointer to a region of memory. And this also knows that there are 4 elements in there, and so we can store them contiguously, but we don't store the contents, really. We store 1, 2, 3, 4 addresses, and the addresses have a fixed length, and therefore we need 64 bytes times 4, okay? And so now you have for each of these is not interpreted as the content of the list, but it's interpreted as a reference to the content of the list, so as an arrow. And the arrows can even be replicated, duplicated, if you want, like in this example in the middle. And here, so let me extend this. So this is still the RAM. It goes on. Okay? And so here, at some point, this arrow is going to point to something that says, I'm an integer, I'm an int, and my value is 3. Okay? Somehow. And here, there's going to be something that says, I'm an int, a Python int, and my value is 7. And here, there's something that says, I'm a string, and my value is hello. Okay? Something like this. Yes?
I'm probably super wrong, but I
Don't worry.
remember in high school doing a lesson on how every single its contents and then point to the next one. So,
well, what you're speaking about is a linked list, I think. Because if you have an arrangement in which each element points to the next one, and then the next one, and then the next one, that's a data structure, which is called the linked list in technical terms. Okay? And it's useful. It's not what I'm talking about. It's similar to what I'm talking about, rightly so. But instead of having each element containing the pointer to the next, we have all the pointers at one location and all the elements pointed to somewhere else. Now, if you think about what this implies in terms of the cost of each operation, now, suppose now that I start like this, and I say, now I want an element in the middle, I want to change it from 7 to 3 to the 100. What do I do? Now, if I want to change this to 3 to the 100, I can just find, first of all, I need to find a bit of memory that allows me to store that 3 to the 100 thing. Big enough, but not huge, possibly. So maybe I store it here. I say, okay, now this is int, and this is very big, but not as big as the whole list. I'm sorry. Let me try again. Okay, so I'm saying, okay, this is an int, and it's 3 to the 100. Okay, and then what do I need to do to change the contents of the list? You just change the arrow. So, for example, this one here, you take it, you remove, you overwrite the contents that were there previously, and you just write the address for the other thing. And you see that all the rest of the list has not been touched. Okay? So this still requires relocating the list if you add things at the end. I mean, if you want to increase the size of the list, you still need to add more stuff here, and then maybe, as we were saying, if there's already something there, you cannot do it, and you need to take the whole thing and copy it somewhere else, and then where there's enough space, just like we said before. But at least this operation of changing and modifying one element, this is now, with this arrangement, is finally order 1. Okay, so this is, of course, there are a lot of optimizations and technical details that I'm been skipping here, but the basic thing is this one, okay, with Python lists, which is what makes them so flexible, but also it's what makes them so slow and expensive, okay, because for each element you need to remember what type it is exactly, and whenever you fetch an element, you need not only one hop, but at least 2. Because you need to go from the start of the list to the position, and then from there, the address and the new thing. Okay? So that's cumbersome. So the other arrangement, this one here, okay, with all the elements tightly packed in a contiguous space, is way, way friendlier for the CPU to access. Because the CPU, in a sense, also for hardware reasons, likes a lot to access things in the same region of memory in sequence. Okay, that's a very fast, it's specialized to do that. Okay, it has a system called caching that takes whole chunks of memory, puts them in a faster amount of memory, and then operates on that. So if you can take the whole thing, put it in this even faster memory, and work on that, it's very, very quick. If all your data is scattered around, then you cannot do this. Okay. That's one reason. Yes? Basically, yes. I mean, okay, there are specialization and optimization for the most common cases so that you don't notice this as much. Say, for example, if you have a list of very small integers, and it's all of small integers, Python has probably a special arrangement for that in order to make them that faster and more similar to this. But it still needs to check every time if that's the case, and just be ready if that's the case to change around. So there are lots of tricks and very neat hacks, let's say, inside Python to try to make this more efficient than it would be from this naive description. But essentially, you can do that in some situation, but in general, you need to go with this arrangement here. Okay, good. Okay, so this is the compactness and uniformity. You see, you can only achieve it with this new type of integers, and this is why ND arrays are homogeneous. They only store one thing, so they all need to store the same kind of data. You cannot mix integers and floats, for example, and they all must be the same type of integer or the same type of float, so all 32 bits or all 8 bits, like this, because it's uniform and regular and compact. Okay? In this way, you can keep all the information you need in something like a header here, and then you're done. And this gives you all the information you need because everything else is implied. The other thing that this helps with is the fact that when you want to do an operation on this, it can be much faster. Why? Suppose that I have, again, a Python list. Not only there's this fact that maybe the list, contains only numbers. Okay? Not only you have to follow all these hoops in order to reach the data. Also, the numbers could be a different type. It could be you have an integer and you could have a floating point thing, for example. Now, what happens if you want to sum? Let's say, if you want. So let's think again. We are starting to think about the hardware, right? So what if you want to compute this as opposed to computing this? Is this the same? Are these two the same? Well, if you try Daum in Python, they give you the same answer. Okay, it's 3.5, and you don't notice any difference. However, inside the memory, this object here and this object here are represented in a very, very different way. Because the one there is represented basically, as we said before, somehow, okay, with each bit representing some sort of multiplier to a base 2. And the 1.0 is represented in terms of the base and exponent in a complicated way, which is given by the IEEE 754 standard, okay, which we're not getting into, but it's a standard in which the 64 bits are arranged with some bits reserved for the exponent, some for the mantissa, some for this one for the sign, and so on. So this 1.0 here and this one here are very different bits inside the memory. And if you want to do the first operation, both of these are represented the same way, and there's some specialized circuitry in the CPU that knows how to compute the sum of those two in one single step. On the other hand, so there's just hardware, okay? You take those bits, the other bits, you feed them into circuits, essentially. They go and physically compute the outcome that comes out again according to the same standard, and you get out the answer 3.5. On the second line, you cannot do that, because if you try to do that, then the one here would be represented maybe something like this, okay, something like this. You would feed this into this machinery, but this would not be, I mean, this would get interpreted as if it were a floating point. It would be interpreted as this was the sign, and then there was somehow the exponent, and then the mantissa or something. Okay, it would get a radically different interpretation. This would represent a number more like 1 to the minus 300 or something, I don't know. Okay, completely wrong result is what I'm saying. So you need to convert it before. You need to figure out that this is an integer, this is a floating point, that between these two types, when I sum them, I need to promote one to the other type. And it means that this here now must be converted to this, I need a conversion step here first, okay? So this is not that expensive by itself. It's one operation again. So it's two operations essentially instead of one, okay, in this comparison. However, if you have a list of 1 billion elements, and every time that you go through this, you, instead of just computing what you need to compute, just like, instead of just feeding everything inside the circuitry, like in the first case, if you, for each element you had to check, okay, what situation I'm in? What type is this thing? Is this an integer? Is this a floating point? Is this, and what kind of integer is it? Is it something else? Okay, and every time that you look at an element, you need to check what element it is, what type it is, how do I treat it, how do I compare it with a floating point, and then do the conversion, and then do the sum. If you have to do all of this, it becomes very expensive. So in Python lists, because they can have mixed elements, you cannot assume in advance that you can do everything quickly. In a Python, in a NumPy array, because you know in advance that everything is, say, floating point, you can just do it without checking in advance, element by element. You just check once. Is this clear what I'm saying? Yes?
I have a curiosity. Before you said that Python, a list is actually stored into a system of 64 bits. And if
yes.
Each index has a bit, this means that in Python you cannot have lists which have length greater than 64. Is that correct?
No. Okay, yeah, let's explain. It's a good question, but the answer is no. So what I'm saying is 64 bits is this. Okay, let's rewind a little bit. Start again from the start. Here I have the RAM represented slots by slot. Okay, and then there are, let's say, a few billions of these slots. Okay, and I said these have indices 0, 1, 2, 3, 4. And you get up to, I don't know, 8 billion. And okay, so you can ask yourself, what's the logarithm base 2 of 8 billion? that tells you, so at some point, what I'm saying is, at the end here, let me draw it. At some point, the RAM is going to end. Okay, there's the last byte there, and this last byte might be, I don't know, 8 billion or something. Okay, 8, 3, 2, 5. It's not like this, but just to. Okay, so it's 9 digits essentially in decimal. Okay, so you want to represent this as bits. How do you represent it? Well, you need to take the log 2 of this number, and see what comes up. And what comes out is a number which is smaller than 64, but larger than 32. I guess it's 30. In this case, it would be 33 or 34. It doesn't matter. Okay. So that means that you need more than that amount of bits in order to represent each possible address here. And so in modern computers, we use 64 bits, which are plenty of. They give you, I mean, lots of possible numbers. So we use 64 bits, and each of these, which is 8 bytes. So in each of those group of 8 bytes can then represent any possible address in the RAM and represent any possible pointer that you might want. Okay, so what I'm saying is that now, when you want to represent a sequence of addresses, you just can assume that you will use 64 bits for the first one, and then 64 for the next one, and so on. Okay, so this is why we need 4 times 64 bits in this example. All right? And so you're not limited. I mean, the length of the list can be up to, in principle, up to the billions. Okay, so you're not limited in that way. There's a question. Sorry, what is the difference between 32 bits and 64 bits computers? Yes, good. So I don't have a drawing of the CPU. Okay, in 32 bits computers, what I just said is not true. So here's the thing. This, all I've said is about the RAM. Then there's the CPU. The CPU has some internal storage to do its own computation. So for example, the CPU can fetch a little bit of RAM, put it inside its own thing called a register, and the CPU has a few of these registers, like 20 or so. Okay, not many, but very, very fast. Okay, so it has these registers, and in particular, one of these registers can store addresses, okay, addresses of memory. Now, up to some point, the size of these registers used to be 32 bits. I mean, earlier it used to be 16. Then it was expanded to 32 when computers became more powerful. And then nowadays they became 64. So if you think about it, if you have a 32-bit computer, it means that your registers in the CPU are 32 bits. And some of these registers need to store addresses, and therefore they cannot store addresses of more than 32 bits, which means that they cannot address memory larger than 2 to the 32, which is 4 billion, more or less, 4 gigabytes. So in a 32-bit computer, a 32-bit computer is capable of operating on the fly with 32 bits at a time, and it's only able to address at most 4 gigabytes of memory, because it cannot reach, for example, to addresses of this size. Okay? In a 64-bit computer, the CPU operates on 64 bits at a time, and it's able to address much more memory. Okay? This is the difference. Good? Yes. Okay. Okay. So this was quite technical, but it's needed to understand what's going on. We will refine now a little bit what we're going to say. Okay. So the first thing. First refinement is that what I've been describing so far is just one-dimensional arrays. So And I said these are similar to lists, but more efficient, more limited in one sense, and way more efficient in another. Okay, so what about now? Sorry. Okay, this thing I can definitely erase it. What about now two-dimensional things? So in NumPy, as I said last time, you can have one-dimensional, two-dimensional, three-dimensional, n-dimensional things. So suppose that you want to store something like 2, 4, 7, 3, 0, 15, whatever, okay? So this, maybe you have a matrix, maybe you have a table of data, it's two-dimensional, it has rows and columns, and you need to store this. And oh, I'm sorry, thank you. Sorry, good. So anyway, you have this table. And now, of course, you need to still fit that inside the RAM, which is not two-dimensional. It's one-dimensional, right? So how do you do that? Sorry? Two arrays. So, okay, so this is good. Okay, so you say, I have a single array here where there's the data for the first row, perhaps. And then what? Then maybe there's another array here. And then maybe there's a header here. And then maybe there's a header here. So this is header and data, and this would be this first row. And this would be the second row. I'm sorry? Exactly. So this gives it, this could be done, but then you would need to have the extra information somewhere that tells you that these two things are actually part of the same thing, right? That these are two rows of the same thing. So yes, it could be done this way, but actually what we do is, again, because of all the computational reasons that I mentioned before, we like to put things as compactly as possible into memory. We want to have them close together. And therefore, we would like to actually have the whole thing in one place, okay? So actually, the answer is not this, but it's somewhat similar. Somewhat similar because what you really do is as follows. You still have this, but now you put all of the data in the same place. But you just say, okay, I put the first row here and the second row here. And then I have a header. And inside the header, now I need more information than before. Before we were assuming one-dimensional things, and now we instead need to have more information inside the header. We need the information about the type. Well, that doesn't change, okay? Maybe type integer. But we also need how many dimensions this thing has. So we don't want, you see this, what I just depicted here, is something with 6 elements, and it could be a one-dimensional 6-element thing, just like before. Now, instead, I want to say the number of dimensions is, in this case, 2. So here, for example, I could have int 64. Number of dimensions is now 2. Okay? Because I have the number of dimensions is 2, this time I need 2 values, not just one length, but the number of rows and the number of columns. So you have the shape, you need the shape, which is a tuple with the number of rows and the number of columns. Okay? So the one-dimensional example would be ndim equal 1 and the shape equal just 6, for example, or 4, like in the previous example. So the actual arrangement here is that these numbers get opened up, in a sense, they are represented here as 2, and then 4, and then 7, and then 3, and then 0, and then 15, one after the other. Okay? This is a convention to go row by row. This is called row major order. It comes from C. One could also equivalently do the thing by arranging things by columns, say 2, 3, 4, 0, 7, 15. Okay, that's one other convention, which is called column major order. NumPy is able to do both, and so that information about how things are arranged is also actually in the header, but normally you don't need to worry about it because by default it uses row major. It's able to use the other one if needed, okay, Python, NumPy.
Why would we need that?
Sorry?
Why would we need that?
Why you
Why
would?
do we need to store it by columns?
Why would you need to store by column? Okay, good. So you don't, it's again only for reasons of efficiency. So first of all, deciding whether to go by row or by column is purely a convention. So there are other languages, for example, Fortran, famously, which is an old language used for numerical analysis a lot, which goes row major. Okay, so it's just a choice that someone has made at some point, and then there's a split essentially between two traditions. And Python follows another tradition, and Fortran, then MATLAB, and then Julia, and then other languages follow the column major order tradition, and Python, NumPy, I don't know, the others, C, and all the others follow the row major. Now, when you transpose a matrix, for example, you invert rows and columns, that's like if you can do both, you can just switch a single bit in the header and say, now this is no longer row major, it's column major. And that's an operation that requires order 1. And instead, if you had to actually do it and keep it row major, then you would have to start moving around all the bits, and this would be an order n or size of that. As you need to do as many operations as the amount of data that you have. So in some cases, it's useful to just be able to work with column major order if needed, in case one of these operations comes up. It's not very common anyway. All right? So let's just assume that everything is row major, because that's the assumption also when you use the library. And so this is how the thing is arranged. Now, can you imagine how this would be done if you had a 3-dimensional array? You can go on from here, right? So a 3-dimensional array is not just one table, it is multiple tables, okay? And so what do? You just store each table contiguously, and inside each table you go row by row, and then in the header, number of dimensions would be 3, and the shape would have 3 numbers instead of 2, number of rows, number of columns, and number of tables. But that's just the extension of this. And 4, 5, 6, whatever number of axes you have is whatever number of dimensions, it goes on like this. Okay? There's still one more complication which I'll leave for later. Okay, but this is the basics. So, now in terms of code, here's what happens. In terms of code, the first line is always import numpy as np, okay? Import in the library. Then you can write something like this. First of all, confusingly, the way you construct an array could be something like this, with np.array. But right away, if you look at the type of the thing, is ndArray. So for some reason, the constructor is called array, but the type is called ndArray. Okay, this is already annoying, but doesn't matter. The constructor then, in this case, has accepted a list. Now, what happens when I do this first line? What's the first thing that happens there after that line has been parsed. Let's break down what happens there. What about 4, 6, and 8? What are those? They're integer, of course, but now we know that we can have several types of integers. Which type of integer are they? int64, another guess? 8. Okay, these are Python integers. The ones that, regular Python integers that are allowed to go to whatever length. Because the first thing that Python does when you read this line is to construct this list. Okay, so the evaluation order here is that first the thing inside the arguments is evaluated, and then is passed as an argument to the function nparray. So first there's this evaluation step. And when this evaluation step happens, 4, 6, and 8 at that point work just like regular Python. And therefore, these are interpreted as Python integers. All right? And the list is created. And this is a regular Python list with the arrangement that I explained before. After that, and only after that's been constructed, the function nparray is invoked. And the function nparray then gets the list, so it gets to the pointer, gets to the pointing to all the elements. It fetches the elements one by one. It notices that they're all integers. First of all, it notices that they're all integers. Python integers, but integers nonetheless. Because of this analysis, preliminary analysis, having gone through all the list, it decides that it's going to create an integer array, an array of integers. The array of integers is going to be an array of NumPy integers, okay? So it's going to be using the default type for integer arrays in NumPy, which in most machines nowadays is 64, it's NP int 64. So it starts with a list of Python integers. It knows that it needs to create a one-dimensional array because this is a list of length 3 made of integers. It will choose to use 64-bit integers. It will allocate as much space as needed, which is 64 bits times 3, plus the header. And it will start writing in the header, okay, this is a one-dimensional thing, or with type int 64, with length 3. And then it will copy the 4, 6, and 8, which were integers, translating them into NPA int 64 things one by one, and put them into memory and arrangement, and arrange them like this, essentially. Well, not like this, just like the original example. This one here. How do we know that it's 64? Well, that's by default, but the way you know how to make sure is look at this. If you read out the first element now from the array, look at line in 4, you get A0, it gives you 4, it prints 4, it returns yes. You get int 32. Yes. Okay. Now, if you again, I'll get to that. So if you write type of this thing, you notice that it's a 64-bit integer in my case, and actually in most cases. Some people always have this int 32 thing. I mean, it depends on a lot of things. Normally, if your computer is int 32, is a 32-bit computer, then it will use 32 bits by default. If your computer is 64 bits, but maybe the operating system is 32 bits, it would use 32 bits by default. If the operating system is 64 bits, but maybe the Anaconda installation is 32 bits for some reason, then it would use 32 bits. I have seen occasionally happen in Windows. Are you on Windows, right? Yes. In Windows, for some reason, sometimes you get 32 bits by default. I have no idea why. It's silly, but it happens, and it's not a problem whatsoever. Okay, so don't worry. It's just that your installation, a combination of some things in your environment, give you this default. You could still use int64, but we'll see that later, if you wanted, but that don't work. Yes?
So imagine we have an array of all zeros or ones.
Yes.
Why doesn't Python or NumPy, the library, doesn't check it automatically that you only need maybe 8 bits, and then it doesn't allocate it as an...
Okay, good. For those, yes. For those at home, the question is, if all, basically, let me paraphrase. If all my elements are small integers, then why would it use 64-bit integers instead of as many bits as needed just to keep it compact? So if in my example that I just gave here, for example, in the slides, all of these do fit in 8 bits, so why would it use 64? Isn't that a waste? And the reason is that there's a balance, because with 8 bits, you're very limited, and now if you want to do operations with these things, it's very easy to overflow with 8 bits. Overflowing means, just like in the slides here, doing computations that go beyond the end. So just this operation here, 7 plus 1, in this silly example, goes beyond the range of positive integers, and it's so-called overflowing. And you also see it here, runtime warning, overflow encountered. So in order to have, by default, NumPy assumes that you want to do computations, that you have enough memory, that you don't want to be, that you are trying to avoid this generally. And so in order to be safe, let's say, and since the computers is fast enough and can deal with 64 bits at a time anyway, and it can do computations with these 64-bit integers very, very quickly anyway. So it wastes a bit of space, such that you don't have to worry later, and such that at a later point I can write A0 equal, I don't know, very long number, still that fits in a few billion. I could write 8 of 0 equal 1 billion and not be worried that I'm overflowing. Okay? Good? So, so this is a 1D array, and it's arranged as we said. Now, a 2D array, how do you construct a 2D array? Here's an example. This time, one way to build a two-dimensional array is with lists of lists. Okay? So, in this example, I have a list, and then inside there's a first list with the first row, and then the list with the second row. Okay? Now, what happens when I do this, when I run that line? The first thing that happens is that this list here, 4, 5, 6, is constructed and stored into memory with the regular Python integers. Then 2, 3, 1, the other list is constructed and stored somewhere. Then a list which contains references to those two lists is created. Okay? So you have first list, second list, then a list that refers to both, that has those lists as sub-elements, and then this is all fed to the constructor. The constructor looks at this, notices that what is being given is a list, that its element, this time its elements are not integer, this time its elements are lists themselves. So it says, okay, this must be at least a two-dimensional thing. Then it goes looking inside those two lists and notices that their contents, first of all, they're all integer, then they're all the same length, so it's valid. So it must be a two-dimensional thing with integers. And then it allocates the space, it prepares the header, saying the number of dimension is 2, the number of the shape of the thing is whatever, 2 times 2 by 3. So it prepares the header, something like this, and then it prepares the memory and writes down the contents just one after the other, like that. And it returns your thing. And so now, when I type A, and I ask NumPy to give me back my array, to show me my array, what you see is this. And this is very, very deceiving, because this that you see here, it looks like the thing that I just gave. It looks identical to the first one, but really, this is just the way it's printed. Inside the memory, the arrangement of the one that we gave and the one that it's actually inside A is radically different. All right? Don't be deceived. This is just a way to represent the thing in a way that is humanly readable. In a nice, so it tries to just print it in a nice way possible, and it prints it also in a way such that you just copy-paste that quickly and put it inside another line. You can recreate that array. But recreating that array would, again, go through all this process that I just mentioned. Okay? So now, how do you get one element out of a two-dimensional array? Well, it works like one dimension, except you need to give two indices. Okay, so 0 and 1 means row 0 and column 1, pretty easy. So you see row 0, column 1, it's a 5. The number of dimensions this time is 2. The shape, as I said, is a tuple, which you read the number of columns and the number of rows and the number of columns. There's also size that tells you the total number of stuff in there. The size, of course, is just the product of the rows times the columns. So you could just take the product of all of this. But, I mean, you can, instead of doing it every time, you just write a.size. And these are attributes, okay? One thing which is written here, also a little bit of jargon. And this is kind of important just because it's so confusing. So I just might mention it. Let's see. Sorry, in which library is ndim? No, okay, so let me answer this question in a second. You're being confused. It's not inside the library. So ndim is an attribute of an object. And the object is A, and A is an array. So NumPy arrays are objects, and like other objects in Python, they have attributes which you can access by writing object dot and then the name of the attribute. And so a.ndim fetches the attribute of the array. So it's something, it's an information stored inside an array. It's not a library function. It's not a function at all, really. Okay, so let's go on. I was saying that that it's pretty confusing, the terminology used by NumPy, but you need to somehow at least have seen it once or be aware of it, because otherwise you wouldn't understand the documentation. Okay, so the jargon here goes like this. The number of dimensions, ndim, is also called the rank. Now, if any of you has done linear algebra, they know the rank. It's completely unrelated. Okay, it's the same word for a completely different, separate concept. Okay, so that's unfortunate. The other thing is that each dimension is also called an axis. So in NumPy jargon, rows are in a table like this. Rows are called axis 0, and columns are called axis 1. If you have just 1D array, then there's only one axis, which is called 0. If you have a 3D array, then you would have an axis 0, 1, and 2. And this is important because we'll see that in a second. Okay. Okay, this slide is there, but I've already said all of this, so let's skip it. Now, so these that I've just showed are a few simple examples that you can try by yourselves and even try other things. Now, you know, this that I just showed are ways to construct an array, basically from lists or from a list of lists. Now, as I've just explained, this is not very efficient because you need to construct the list first or the double list first, and then that's fed to the array. So this is just one quick way to construct an array, but there are quick in the sense of quick from the point of view of the programmer, of typing stuff. However, when you want to create an array, there are quicker ways. And the quicker way is essentially to prepare the space for the array without filling in the data necessarily right away. Or maybe, so the quick way is to first prepare the space in memory and so give the array the number of dimensions, the type, the shape, and whatever, so that the memory can be reserved, allocated, prepared, the header can be written, and then later maybe you start writing inside the array. Okay, that's way faster. So these functions here are all constructors. The first one is the easiest one. If you write np zeros and you give it a tuple, it builds an array which is filled with zeros. So let's have a look at a second. Now we can start doing some demos in Spyder. So I'm opening Spyder. Okay, let me enlarge here. I hope it's visible. I don't care about the update. Thank you. Okay, so import NumPy as np. Good. Now a equal np array. No, np zeros. And then I can give it a tuple, just like it was in the slides. And you get this. And if you try to print it, you observe this. Now observe what's the type of the elements. So A0, A00, it's the first element. And I'll speak about that, the previous line in a second. A00 is the element at the top left corner. And if you want to know its type, it's a float 64. So by default, if you just write zeros and don't specify anything, it gives you floating point because that's just the most common thing to do. And it gives you 64 bits floating points, because the most common thing for numerical analysis is that. If you want to change that, you can say this. And now A, as you can see, has built in my computer an int64 bits. Okay, so one thing to notice. I specified the type as just int. Now int is the type of regular Python integers, so in a sense this is tricky. It's not being taken literally by the constructor, by the NumPy constructor. It's being taken as to mean, give me some integer type, the default integer type. If you want to be more specific, and if you actually want, let's say, to use uint8 because you want to analyze images, for example, or something, then you write np.int8. You specify the type exactly. Now, if you print, if you display the thing, notice that it looks like the one before, but because it's not the default, it also tells you, look, these zeros are not the default zeros. These zeros are uint8. Okay, so it's helpful in a sense. And you see, sorry, I should have used uint8. I was talking about uint8, but it's of course the same. Okay, and now if I write A00 plus, equal 300, well, equal 3, I can set the first element, okay, and I can fetch it like this. And if I write 300, of course, I get 44. Clear, right? Anybody surprised by this? I just tried to set the element to 300 and it got me 44. What's the explanation? The type. It overflowed. That's 300 minus 256. So it went up, tried to go up to 256, and then starts over again. So this is how it works. Please notice that we did not receive any warning whatsoever. What it does, whatever you try to put inside there, it tries to convert it to the type. So again, please be aware. This line here, how is this executed? The execution always starts from the right-hand side of the equation. So of the assignment, sorry. So the 300 there is interpreted as a standard Python integer. That stores 300. And then, however, it says, okay, now store that inside this array. And that calls a function, a method of the NP arrays. And that method takes whatever you give it and tries to cast it, to convert it, to make it fit inside the type of the array. Because the type of the array is immutable, it doesn't change. It doesn't change the type of the array, it doesn't notice that, oh, there's something that doesn't fit in the array, so I change the type of the array. No, it changes the type of what you gave it, okay? The type of the array that never changes. Well, almost. It could be useful, but it would be very expensive. And so you must be aware that this library is nearly always trying to do the most efficient thing possible, okay? Nearly always. The philosophy is that you should know what you're doing, and that it's trying to do the thing which is most common for the purpose of numerical analysis, which is in turn most commonly the fastest thing, okay? And if you don't want to do that, you need to do it yourself. It's in a sense, so all of these are decisions taken by the creators of the library. They just arbitrarily decided on some conventions like this. You need to know some of them, and in most cases, let me give you this advice, and then we'll have a break. So general advice about all of these things, because it's very, very common that these subtleties pop up when you work, and you probably cannot know all of them, okay? All of the subtleties, all of the things that might happen. It's it takes possibly years of experience to know really all of them and have them committed to memory and feel like they are natural. Most of the times you will be wondering, what if I do this? Is this going to convert this to int64? Is this going to do this or that? You don't know. So the right thing to do is not doing and hoping for the best, is always go to the console, write down a little example for yourself, and do experiments. Always experiment on the console whenever you are dealing with something that you're not 100% sure about. Whenever you're doing something even slightly complicated, go to the console and do a little test and check that it works as intended, as you think it would. Because it's very, very common that you think it would do something and it does something else, and it completely derails all of your code. So, for example, something like that, okay, maybe you are working with an image, maybe you have the color of something stored, maybe you do an operation, you sum two colors, or I don't know, you multiply the color by some amount to just make it brighter or something. You get out a number which goes beyond the limit, like 300. You try to fit it inside the image, and instead of getting a brighter image, you get a dimmer image. Okay, it goes completely wrong. These things happen. Okay, well, they happen especially with this particular thing happens especially with small integers. And with 64-bit integers, you normally don't need to worry about that. But you need to worry about other things. So please experiment with code that, as you will see, I also do it all the time. So it's a practical matter. Okay, so I think we will have a 10 minutes break. Okay? Please try to be around here before 12. So let's make it 10 minutes. At 12, we'll start sharp. Okay? Okay. We should start again. Please take your seats. Thank you. All right, so there was a question. I'm sorry. We're starting again. Hey. Yes. There was a question during the break, so I'll just trying to clarify what went on with what we've just seen, just to be extra sure that you got it. So if you have the number 300 and you want to represent it in binary, you can say that 300 is equal to, in powers of 2, is 256 plus 32 plus 8 plus 4. Okay? Do the computation. So now what we were trying to do is store 300 in a slot of NP uint 8. In NP uint 8, we have 8 bits at our disposals. And these 8 bits represented here, they are interpreted as 2 to the 0, 2 to the 1, and so on up to 2 to the 7, which means 1, 2, 4, 8, and so on up to 128. And so if you start to store it, you see, okay, the position. So look at this and say, okay, there's exactly. So the 4, yes, give me a second. The 1 is 0. The position at 2 is 0. The position at 4 is 1 because we have the 4 here. Position at 8 is 1 because we have the 8 here. Then this is 0. Then 32 is this one. 64 is 0. 128 is 0. And what about this? What do we do with this? Where do we put it? There's no space. We have no room for that. We just throw it away. That's what NumPy has done. It has thrown away this thing here, discarded. So what you're left with is this here, which is 32 plus 8 plus 4, which is 44, which is what we got as an answer before, all right? So if you try to fit something, shrink it into a space where it doesn't fit, all that's left is simply thrown away. Good? So this explains what we have here. Okay, so having said that, okay, this was perhaps interesting, but also very technical and possibly a little bit dull. So for the last part of the lecture, I think I will try to give a few demos and try to, say, embark on a little bit of a project that we'll carry on later. I mean, we'll still have to cover a little bit of ground in terms of how NumPy arrays work, but let's start working with them at least to get a feel of them, all right? So first thing I want to do is to actually demonstrate in practice how the fact that I've repeated over and over, which is that NumPy arrays are way faster than regular Python lists. Okay, so also, I have mentioned in one of the earlier slides, maybe you don't even remember, but I'll repeat it again, that NumPy also comes with its own random generation library, random number generation library. Do you know about random numbers? Pseudo-random numbers, I should call them to be precise. Okay, so in regular Python, what you do is import random, okay, in regular Python, and then you have access to things like random.rand, sorry, random, I guess, yes, and this function here returns random floating point values between 0 included and 1 excluded, okay, uniformly distributed in this range. Okay, so you call it repeatedly, and you keep getting new numbers between 0 and 1. Okay, this is how it works. So now suppose I want to generate an amount of those, let's say 1,000 or 10,000. So what do I write? Well, let me give this file a name, first of all, save as, and I'm going to call it, let's say, nope, sorry. Where is it? Okay, this is kind of annoying. Oh, here it is, sorry. This one, nope. Here, SciPy intro. Okay, so let's call it, say, sorry. Let me call it some speed demo, okay? Random some speed demo, okay? Because what we're going to do is to generate a few random numbers and then try to compute their sum. And just see how long it takes to generate them and how long it takes to compute all the sum, just for a demo of the speed of it, to compare the speed of the two things. So here, I would say import random, let's say, and now I want to say I create a variable, number of values. So let's just call it n, and it could be, I don't know, 100, and then we change it and make it larger. And then I suppose that I want to create a list, a regular Python list, with 100 random numbers using what I just been using here. How do I do that? Create a list with these things, with 100 of these things. A comprehension. Good. That's the quickest thing to type, which is doing random.random for I in range n. Okay, something like this. Okay, so this should work. We can try to run it and check whether L is actually a list of random numbers. It is. Good. Now, how do I time it? How do I find out how much time it took for that line to run? Well, there are various ways. The easiest way, it's imprecise, but it's good enough for our purposes. The easiest way is to exploit the timing library, so the clock of the computer. You look at the clock before you execute the line, you look at the clock afterwards, okay? So that you find in import time, and in the regular Python library time, and this gives you a number when you call inside that library, when you call the function, which is also called time. What number? If you call it again, you will notice that it's close but slightly larger. Okay, anyone has any idea what this number is? The clock, yes. How is it? Unix time, great. What's Unix time?
It started in the 70s.
Yes, okay, good. For those at home who haven't heard, the answer was Unix time. And what Unix time is just a conventional way to measure time, which is start from the 1st of January in 1970 and count the number of seconds from there. So if you do that, you say this is seconds, this is minutes, this is hours, this is days, this is years, this is years. It's roughly 51 years, as you can see, because it's 51 years from the 1st of January of 1970 plus something, almost 52 years. Okay, good. So that's the meaning. Now we don't care about that, but the thing is that if now I say, okay, here import time, and I say the time at the start is time.time, and the time at the end. So the time difference, so rand gen time, what is it? Is the time right after that minus the original one. You see what I did? It says run, tell me what time it is, then run this line, then tell me what time it is again, but subtract the number of seconds at the beginning. This gives me the gap in seconds. Okay? And then print Python rand generation time equals rand gen time. Okay, let's run this. 1 to the minus 5. That 1 to the minus 3 would be a millisecond. So it's 100th of a millisecond. It's actually, therefore, 10 nanoseconds, I guess. Pretty fast. Okay, but now suppose I try to do 10,000 numbers, and it takes 1 millisecond. Okay, what if I do 100,000 numbers? It takes roughly, I mean, if you run it again, it's going to change a little bit. What's happened? Okay, I guess this just crashed for some reason. I don't know what happened there. Let me restart the kernel. Okay, I'll run it again. Well, $100,000. It's more or less 100th of a second. It changes from time to time because it's not deterministic, the exact amount of time, because there's other stuff going on in the operating system. Okay? So, what would be a more precise way to time an algorithm? That's a complicated topic, exactly because there's stuff going on in the operating system, so you would probably need to just run it a few times and do an average. And a careful average, being careful that you reinitialize the thing exactly as it was at each time, each iteration, and also there's nothing else going on in the computer that might affect the timing, just like, I don't know, playing a video game. In the meanwhile, I don't know, something that occupies the CPU. There are also ways to, in principle, to detect how many CPU cycles have been dedicated to exactly the process that you're running, but we'll not get into that. And I'm not even sure that you can do it with Python at all. You could do it with other languages. Anyway, you could ask the operating system to tell you, but not inside Spyder, let's say. Okay. Okay, so I was saying that NumPy, import NumPy as NP, import NumPy as NP. Okay, NP random is a submodule of NumPy. So this is a different random library which lives inside NumPy. And you still have this function random, which still behaves like the one before, like one we've just seen. It has generally a better quality of random numbers, but we won't care about that. Better quality means that it's closer to doing what it's supposed to do, which is produce numbers evenly distributed, uniformly distributed in the range. The regular Python one is slightly worse than that. It says, but this one, let's ignore that. Let's say that they are the same. What's the difference? The difference is that now if I do np.random.random10, if I give it the argument, then instead of generating one number, it generates 10 of them. And not only that, you will notice that it has put them inside an array, which means that they are arranged compactly and nicely in the way. So this is an array of what type? What's the element type of this? What's the element type of this array? What would you guess? Okay, float, okay, and the array is the type of the array, but I'm asking about the type of the elements, which is indeed floats, but is it floats really? So let's see. If I do one number, NumPy float 64, the type of this is float, which is a regular Python float. The type of So if I take this and give it a name and say A0 and ask for the type of A0, it's NumPy float64, which is almost the same thing, but not exactly precisely identical. And we can mostly disregard the difference, ignore the difference, but just to be precise, these are slightly different types, okay? Mostly the same. In any case, so what this says is that now I can try to compare this part here and do the same thing, but this time instead of L, I use A. Instead of random, I use np.random. So I need to import NumPy as np. Okay. So np.random, instead of using a comprehension, I'm going to just give n as the argument. And I'm going to say that this is np run_gen time. Okay. And then I copy and paste this line here. I'm calling this NumPy run_gen time, and it's np run_gen time. Is it clear what I did? Good. Let's run it. You notice that there's one more 0 down there. It's 10 times faster. Okay? And of course, they are both pretty quick. If you don't really care much about the time, you might as well use the first one. But if you're doing this repeatedly 1 billion times, which might happen in some applications, then this starts to build up, and having something which is 10 times faster helps a lot. Because maybe instead of 10 hours of computations, you do 1 hour, okay? Which is the difference between wasting one whole day doing something or being able to go have lunch, go back and have your result, okay? Good. So, so this is just generation, just producing numbers. Now let's check. As I said, I want to compute the sum of them. Now again, I'm going to copy and paste these lines just because there's the timing stuff. But instead of timing the generation, now I want to time the summation. So S equals sum of L. This is regular Python, right? I have a list. I call the function sum of it, and I just compute the sum. And this, now I have timed it because it's sandwiched between those two lines. Yes. Let's see. Sorry, why does my Python round the numbers to the first decimal? It prints 0.0. No, it doesn't. Sorry? Your 32-bit does 0. Yours, also yours.
Yeah, I get 0.
What, sorry. You get 0 when you do what exactly? Did you write, I mean, did you write exactly the same thing as this one? This is weird. You should, what you should do, you should write T0 equal time.time and then T1 equal time.time, and then print both of those and check whether they are equal. They should absolutely not be equal. Or I don't know. Or maybe, you know what? I think I understand. Now it occurred to me. The time routine, the time function, of course, asks the time. How does it know the time? It asks the operating system. The operating system asks the piece of hardware which is the clock of your laptop, okay, which stores the time. Now, some laptops, some hardware, have a limited precision. They don't go beyond, say, 1 nanosecond, I think, or 1 millisecond. Yes, I think that's it. This is the answer. Some hardware has only a precision of 1 millisecond. And therefore, if something is quicker than that, you don't see it. And because this task is so easy and so quick, even with regular Python, we've seen that it takes, I don't know, really not enough. It takes a small amount of time. It's not detecting the time with enough precision. That's the clock of your computer. If you do something which is, you could try to do this, to do time.time, then wait a bit, then do it again, and check whether it actually increases, and also check what's the precision there, if you see these many digits or not. Possibly yes, because it's going to convert from float. Yeah, it's the same digits, but if it's too quick, then you're going to get the same answer twice in a row. That's my best guess for what's happening. So try to do something else in the middle here. I don't know. Make it longer. Make it 1,000,000. Try to make n larger. Yes, exactly. So yes, now with 1,000,000, it should go at least beyond millisecond range. Okay, so yeah, let's move on, assuming that this is solved issues. What? It fixed the issue. Good. So okay, yeah, it's the hardware. Or the hardware or the operating system. It might be the operating system. It might be that your Windows is not precise enough when it gives you the time. It happens. Anyway, so the summation time here is this. What if I try to compute? And now I claimed over and over that arrays are faster. So let's say array sum is the sum of the array. And then I'm saying NP sum time. Okay, and then I want, I want to copy and paste this one and just have numpy here and here NP sum time. And of course, it's going to be very much faster, right? Well, if I had, as it's not a valid. You see this error? It's an invalid syntax because AS is a keyword in Python, so I shouldn't use that. So let's say SA, I don't know. We don't need to be, so this is fine. Okay, so is this quicker? It's horribly slower. What happened? Have I been lying to you all this time? Of course, yes. Can all go home. Stop dealing with this. Could then be a problem for future tasks? No. The question is about the time function, if that's not precise enough. No, it's not a problem for future tasks. As long as you understand this issue, you will not have this problem at all. And this is just a demonstration. I normally don't give time in tasks, let's say. But if you're trying to do this for your own purposes, to time your code, then be aware that your hardware is not precise enough, evidently. And just do something more time-consuming to actually detect the times. So going back to the issue at hand. Here what happened is I called the function sum, the Python function sum over an array. Now an array is very compact and very friendly to the hardware, but sum is a generic Python function. It's very, very generic. It's applicable to any iterable object. It can sum lists, it can sum whatever you give it, as long as it produces, as long as it can be iterated. So it's very generic, and it was built Python. It's, sorry? No, sorry, I couldn't hear. Cum, sum, C-U-M? No, that's a different function. That's cumulative sum. No, the answer is correct. So this function is correct. Yes, to make it faster. Let me try to explain what's going on here. The reason why it's not fast is that because it's a Python function, it's generic, and it's so when it finds an array, it's not exploiting the characteristics of the array. It's not exploiting this fact that it's stored like that. It's actually taking all the time to ask the array for each number in turn, and then the internal machinery of the NumPy arrays returns one number after the other. This is quite slow. For lists, it's faster just because this function sum has been specially optimized to work more quickly with regular Python lists. Okay, but its sum is a very slow function. However, look at this, np.sum. There's a different function that lives inside the NumPy library. It does the same, but this one has been written by the authors of the NumPy library, and it knows about arrays, and it knows how to sum arrays quickly. And now you run it, and you see that again, there's one more zero here in front compared to the one above. All right? Again, a factor of 10 more or less gained, even possibly, oh well, around about a factor of 10. Okay? So this is a very tricky thing and something that you forget all the time. I certainly forget about it myself often. When you are trying to compute the sum of an array, use np.sum and not just sum. Alternatively, you could also do it like this. Instead of np.sum, you can have a sum. So sum is a function inside the NP module, this one, but it's also a method of arrays. And they are exactly the same thing. It's just two alternative ways. This one helps you not forget, helps you avoid to accidentally use the other one. Okay? So, okay, I run it, and of course it's the same. Okay? Good? Are there questions before we move on? This was just a little demo of how, in fact, arrays are faster than lists. If there are no questions, we can move on to a different task. Okay, so let me explain the idea first. Where's my... it stopped. Yes. Wonder why. Okay, there we go. Okay. So, here's the idea. Do you know about Monte Carlo algorithms? Have you heard of Monte Carlo algorithms? I think most of you have. We are going to implement a very, very silly, small Monte Carlo algorithm. So, what do we do with that? We try to estimate the constant pi, 3.14 and so on, with Monte Carlo. Okay? Of course, if you go to NumPy and you write np.pi, that's it. No need to do this at all. Somebody has already done it for us. But we'll do it as an exercise, of course, to demonstrate something. So how can you estimate pi using Monte Carlo, which means exploiting a random algorithm. This is one way. You take a square of size, let's say 1 by 1. Okay, so this is 0, 0, this is 0, 1, this is, this is 1, 0, this is 0, 1, and this is 1, 1. All right, coordinates. Good. Then take a quarter circle like that. So it's a quarter of a circle of radius 1. Okay? And so what's the area of the quarter circle? Well, the area of the whole square is 1, of course. The area of the quarter circle, what is it? Pi/4. Great. And so Now suppose that I was able to draw points in the square at random uniformly, a rain of points like that. Tac, 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 tick. Okay, so just dots uniformly, randomly inside the square, something like that. Okay, I have drawn a number of points. Now, what do you expect? If they are distributed randomly, uniformly, then you expect that the fraction of points that get inside the quarter circle is exactly as the fraction of the quarter circle area divided by the total area. So the expectation is that on average, you would say this, I'm using these brackets to denote the average, and I'm saying that the points in the quarter circle divided by the total number of points is about, well, the expectation is exactly the area of the quarter circle divided by the area of the square, which is pi/4. Okay? Which means, in turn, that we can have pi is about, if we now do it in practice, and we actually do the experiment, you can say that pi should be about 4 times the number of, well, let me say the number of points, okay? Number of points in the quarter circle divided by the total number of points that we have drawn. Okay? Good? Yes? Oh, sorry. Thanks. Good? Okay, so let's do it. The first thing we try to do, first thing we want to do, let me reset everything here so that we start from scratch. Start the kernel. Then also I will save this file with a name, which is Monte Carlo demo, I don't know, something like this. Import numpy as np, just not to forget. So the first thing I want to do is actually plot the square and the quarter circle. Just, well, start from the quarter circle. So in this way, we also start demonstrating the plotting stuff. Okay. Now the line for that is import matplotlib.pyplot as plt. And okay, so in the first one of the first few lines, first few slides, we had demonstrated. Well, let me do it just a little bit. 0, 1, 1, 2, yes. Okay, good. Let me close this. I'll reset just because I want to do things in the right order. Okay, if you remember, one of the slides that we had earlier was this one, in which we said the plotting function takes a list of x values and then a list of y values, and then by default it plots them by connecting the points with lines. Okay, this is what we have. How do we plot a circle, a quarter circle? We only have straight lines. What do we do? Well, you say you want to check if the coordinates are obeying some equation according to Pythagoras theorem, I guess, but the basic thing is we only have we can only plot straight lines, and we want to plot a circle. What do we do? We'll make small We'll make small segments, straight segments, and if they are small enough, it's going to be indistinguishable. All right, so that's the first thing. Okay, so we want to plot a polygon, really. Okay, and then make the size, number of sizes of the polygon very large. Okay, so what we're going to do is, when we plot this, we want to actually to find the points. Let's say that we divide it in 1, 2, 1, 2, 3, 4, I don't know, 5 points like that to start with. Okay, so those 5 points that I've depicted there in green, can you see them? Okay, so we want those. How did I draw those? I've drawn them in the picture, if you notice, more or less such that there's a constant angle, right? So this is a hint. I want to start from angle 0 and then start in regular intervals up to 90 degrees. And so I need to divide the range from 0 to 90 degrees into a bunch of angles, into angles all of the same size. And if I have the angle, like this one, let's say, let's pick this one here. If I have that, then what are these its coordinate? I know the angle, well, I just need some trigonometry. I have this angle here, and I just compute the cosine to get the x-axis, and the sine to get the y-axis, right? And so for each of the angles that I've produced, I compute sine and cosine, and that gives me the coordinate. And then these I have now all the x and y's that I need to do the plot. Okay, let's do that, and let's do that in regular Python. So number of circle points equal 5, let's say, to start with. Let's check that what we're doing is correct. Okay, so then I'm calling the angles theta. So in regular Python, you would need to take the range from 0 to pi divided by 2, which is 90 degrees, and then divided that range into 5 chunks. Instead, what I'm going to do is exploit one function that I have not spoken about yet, but it's a nice one. You see, of course, this is now a trick. I'll write it and then I explain it. Okay, so import numpy as np. Okay, np lin space between, let's say, 0 and 2, 5. What does it do? This, first of all, it's a numpy function. It gives me arrays. Second of all, it takes these 2 points and treats them as the endpoints, 0 and 2. You see, the first and last element of the array. And then it says the array length should be 5. You see, 0, 1, 2, 3, 4, 5. And the elements in between are linearly, which means equally spaced. If you take the difference between each of these 2 points, it's 0.5 in this case. It has divided the range between 0 and 2 included. This is not like Python ranges. Here, the endpoint is included. And it has created an array of 5 equally spaced values between these 2 extremes, which is exactly, precisely what we need. Okay, and so what I wrote here is between 0 and pi halves, and I want these many points. Okay, and so now I can plot, I can say the x's and the y's. Okay, I'll need 2 lists, let's say. Let's start with lists. Okay, and I'll say for t in theta, so all the angles that I just computed, I can iterate over them. It's an array, but it's still iterable, so I can put it in a for loop. All right? If I do this, and then I say the x, as I was saying, is the cosine of theta, except that, look at here, undefined name cos. There's no cosine function in regular Python. What do? you import math and use math.cos. But now we use np.cos. There are basically all the mathematical functions that you had before, you now have inside np. And why is that? We'll see it in a second. But we can use it, and right about now, this is just the same as regular math dot function, okay? The same, think of it as the same for now. And then I say xs dot append x, and then I say ys dot append y, and this now should have given me all my coordinates. So plt dot plot, and then x's, and then the y's, and let's see. Okay, so first of all, possibly many of you will be seeing the plot appearing here on the panel on the top right. This is just a setup that I have in my own system to plot it in a different window, but doesn't matter. The other thing is that probably you see it distorted like this. It doesn't look like a quarter circle, but that's just because the ratio is different. If you just make it such that 0, 1 and 0, 1 here, the x and y coordinates are the same length, then it starts looking a bit nicer. Of course, this is a crude polygonal approximation. Now that I've seen it work, I can change the number of points to, let's say, 100, which is absolutely plenty. And I plot it again, and here we go. And as you can see, just like I mentioned last time, if you call the plot command again, what you get is a new plot on top of the old one with a different color by default. Do you see the new plot in orange? I see some perplexity. What was the question? No, there's no question. I was just wondering if everything is clear so far. I see some doubt going around in the room, let's say. Sorry? Well, what about the second plot? Do you see the orange one? Do you see the double? Okay, that's probably the new spider or something that does this. In any case, doesn't matter, because the solution to all of this is that we don't want to call the same plot over and over. You want to say plt.clf first, so clear everything, clear the figure, and then start plotting. And this, now, at least in my case, it produces a nice blue circle. And if I want to make it similar to what I have here, that is plotting it in red, how do I say that? That's super easy. You just write the string R there for red, and it understands. Okay, it's plotted in red. And if you want to be more verbose, you could even write red, I guess. And if you want to be even more verbose, you can say color equal red, and these are all equivalent so far. All right? Okay, so various options here. The most synthetic one is just put an R, a string R there, and it understands, and plot understands that you want to mean that it's red. Okay, the other thing. How much time do I have? 5 minutes? Yes. Okay, so before we go on and actually implement the Monte Carlo algorithm, which we will do next time, I guess, I want to demonstrate this. Theta was an array, right? And we have been using it as if it were a list. np.cos and np.sin are NumPy functions, and we have been using it as if they were regular math functions. instead, what we could have done is this. Look at this. NP dot cos of theta. And ys equal NP dot sin of theta. And now I take all of this and I comment it out. Okay, so let me explain what I did. First, let's check that it works. It does work. Okay? So let's check, let's see. Let's think about what happened here. Theta is an array. So you're trying to compute the cosine of an array. Mathematically, that doesn't make any sense whatsoever. Right? The cosine mathematically is defined as a function over one real value that gives you one real value. But NumPy np.cos has a property, has a behavioral property, let's say, which is called broadcasting. And this is going to be a big topic for the next lectures as well. So broadcasting means, in this particular instance, it just means that if the input to the function is an array instead of a single number, then the function is applied to each element of the array, one after the other in turn, and the result is stored in an array as well. And this is super efficient because NumPy knows in advance that when it sees an array, the result must be an array of the same length, so it allocates the memory all at once. Okay, it prepares the output array immediately, and also it starts going through the values in the original array and applying the function to all of them one by one very quickly because of this compact representation that we spoke before, and it starts to output them also in another portion of memory which is all contiguous, and so it's all very quick and efficient. And you want to see what is excess. Excess is, of course, as you see now, it's no longer a list. It's a one-dimensional array. Now, this works in general. So this is the real difference between the NumPy version of the functions and the math version of the functions. That if you try to do this with math.cos, it would tell you, I don't know what to do with this, because math.cos expects real numbers. Instead, NumPy.cos can handle arrays and be efficient with that. And it also works in general in the sense that if you give it any array, even a two-dimensional, three-dimensional, whatever dimensional array you give it, you can call np.cos, and it will return an array with the same size and the same shape with the cosine computed element by element in the corresponding positions. Is it clear? Okay, good enough. This is intuitive enough, but it's the first example of something that will become more complicated as we go along. This is called broadcasting. Okay, it's very useful and very, as you can see, at least at this stage, is very compact as long as you know what's going on. Okay, and this is an array, and of course, notice also that pyplot is able to plot arrays. Just as a side note, it's actually better for plotting to give arrays rather than lists, even though it works in both cases. And I think we can stop here for now. Yeah, and then we will do the random numbers generation and then the estimation of pi. Okay, I'll stop the recording. Let's see how we do that. Are there any? Yes, sorry, before I stop the recording, let me just address the fact that I've seen right now some comments on the chat, but we've already spoken about those. Okay, see you on Monday. Goodbye.